Alright, time for another draftphysics.com, debatephysics.com also. Video presentation. So I already made this video, so I am going to just play, my other video. The audio didn't record, so just really irritating. So I'll use my little arrow, I guess, and I can point to things. So anyway, so kinetic energy, yes, the claim just keeps being made that levers don't conserve momentum, and that you would say also pulleys must not conserve momentum. And it's just silly and stupid, and people shouldn't be defending this idiotic premise that momentum isn't conserved. Now, obviously, they already had they already had a conservation problem. In the sense that levers change the direction, and direction is supposed to matter somehow. And clearly there's no evidence that twice the energy goes into the fulcrum and into the ground or any of that kind of garbage. And, you're getting 100% of, theoretically, ideally, of what you put in, and you get a completely reverse direction, and that makes perfectly good sense. So a 2 mass goes in with one velocity, a 2 mass at the same distance should come out, and at twice the distance, by Archimedes math, you should get a 1 mass going 2v. Now they're claiming, the new modern physics is claiming, that it only comes out with 1.4, and that you could put a 1 mass going 1.4 in over here and get a 2 mass going 1v pop out over here, gaining 33% more momentum, free momentum. So in one direction you lose 30% of the momentum, the other direction you gain 30% more momentum. Ludicrous, stupid. I shouldn't have to argue it. It's MV in, MV out, and there's no violation of conservation of momentum, and they really shouldn't argue for it. And again, the pulley kind of proves it, because pulleys clearly there's just no choice when you look at it, right? I mean, it's 2 pieces of rope, twice the amount of rope moves, and so it just has to have that relationship of 2 to 1 in terms of the amount of motion you can create. This one has to do twice as much as this one, as the other one, and there's no way around it. So there shouldn't be any argument about levers conserving momentum. If pulleys conserve momentum, then levers have to conserve momentum. So why argue? So all of this comes down to this idiotic statement by them that it takes 25 times the fuel or force to move something 5 times as fast. And that's just junk science. It doesn't happen. There's no evidence of it. They can't show you an experiment demonstrating it. So the Mythbusters did crash the cars 100 miles an hour, 50 miles an hour. Supposed to be 4 times the damage at 100 miles an hour. Only twice the damage. Only conservation of momentum again. No evidence of conservation of kinetic energy. No evidence either that it took 4 times the energy to move the half as massive car twice as fast. No evidence. No, same car, sorry. That it took 4 times the energy to move the car twice as fast. But they didn't measure that part. But there's no evidence of it. And there certainly isn't any evidence in your life experience of this quadratic increase in the amount of energy it takes to move something, a speed. And gears, you can go through ballistic pendulums and go through all these different examples. They're all ignored by any one of the critics. So in here I'm drawing springs to say do all of these experiments flat. So get them out of gravity. So the idea would be is to create an oscillator. So you put a spring on either side of the balance and then oscillate it. And again, you'll get the same result where the 2 mass will move 1 unit of distance, the 1 mass will move 2 units of distance, and it will oscillate for quite a while. Don't know exactly how to make an oscillator out of pulleys, but sure it's doable. Just put springs on them, I guess. So I should think about that. So anyway, the point of the video is that I will provide a couple of examples of experiments that I think might help get to the truth, get rid of some of the variables. So again, we've seen some experiments, where they use plastic cars with little metal wheels. Very bad idea, where they launch things with springs and have the expectation that springs are even, that springs launch things with the same energy no matter what speed they're going to move. And you could obviously sort of understand that a spring moving very quickly will still have very quickly it's still moving very quickly when the object leaves, so the spring will oscillate more after the experiment, indicating it kept more of the energy. So the lighter the object you put in front of a spring and launch it, the more energy you're going to leave behind in the spring. So lots of experiments have variables that weren't anticipated or corrected for or understood at the time of the experiment, and it really matters. You could go back all the way to Madame Chartelet and denting clay with round objects, and how it makes a huge difference whether you dent the clay or whether you penetrate the clay, because basically round objects, depending on how deep they are, change their shape. So they go from being a very flat thing, if just a tiny bit of it hits, it's very flat, the bottom, to being a very sloped thing, the deeper you go into the clay. So this could logically be understood. You can't do the experiment with, you don't have the expectation that you have the same energy and you're going to shoot an arrow with a little ball bearing at one end, and then you're going to shoot the arrow with a point at the other end, and that they're going to penetrate the same distance into the object. That would be a silly expectation. So clearly one of them doesn't have more energy, just one of them has a better contact with the substance, and so it has more capacity to penetrate the substance, break it. It's not going to move more mass, more velocity. It's just going to take advantage of the fact that it can break a surface. So all of that has to be understood, right? I mean, you don't go smashing crackers and silly experiments where a certain amount of energy and the whole thing crushes, and right before that it doesn't move at all. Alright, so here I am showing the first example of an improved experiment, I think. And the idea is to do the lever launcher. Okay, so you just got a spring over here and you're going to push something. So this is all horizontal. So again, this is like looking down at it from above. And instead of launching, just have the masses attached. And so then you can use the same exact object, have two of them here, one short of the distance, one a little bit further out, and then one mass at two distances. And what you all you have to do is measure the speed of the lever itself. So if you film it exactly from the same camera position, you could just superimpose the two experiments on top of each other and see if the lever moves exactly the same. And if it moves exactly the same, then that's basically telling you one mass creates twice the velocity, two mass half the velocity, and proves the point that you're going to conserve the momentum. Now the interesting thing is the fulcrum, because if you put counterbalancing weights, the absolute weight of the experiment would be much larger here, right? If I have a 2 mass over here to compensate for the 2 mass here, you can sort of understand, okay, that balances, but that's going to be more weight than if I have a 1 mass and a 1 mass. That's a heavier, lighter experiment. So the fulcrum, whatever you're using, would experience more weight. So that it's better not to have the counterbalance and just force both of them to have the same imbalance of weight. So you could argue that when it was sitting on the fulcrum, whatever this weighs, this 2 mass at one distance and this 1 mass at this distance, both sides are going to experience that same weight. So the fulcrum will have the same tension on it, which is important. So you want to have the same tension on the fulcrum, you want to have the same amount of friction in both experiments, and you want the spring, obviously you'll do the same expansion of the spring. But anyway, so it's a way of doing the experiment that just eliminates all this stuff. Now obviously if you have a timing gate, you could just put a little card on the end of the fulcrum, and at the end of the lever, and just measure how fast it goes through the And it's, as long as you put it in the same exact position, it doesn't matter where it is on the arc, because the acceleration is going to be the same for the lever. Accelerating the two mass at one velocity, it's going to take exactly the same time as accelerating the one mass at at two velocity. So that should clarify. That should be a clearer experiment, cleaner. But you don't have to worry about rotation. We don't have to worry about skidding frictions. We don't have to worry about pendulums and heights. We don't have to measure. We don't have to get the instantaneous liftoff velocity. We don't any of that stuff. You're just going to measure the lever. The lever will tell you whether the two things are moving proportional to the law of the lever, whether Archimedes was right. So it's just a test of Archimedes. As a scientist, was Archimedes smart or stupid? Because this arc will be exactly the same in both experiments. Whether the mass is here or not, or the mass is it doesn't matter. It's just about the fact that these two things absolutely do weigh the same. It's the same amount of force to move them. So moving the one mass 2v is the same as moving the two mass 1v, and the fact is momentum is the only thing that matters in the universe. So here I'm just talking about extending the lever and balancing, and how it's really unnecessary, and it probably doesn't make the experiment better, just because the total mass of the experiment changes. Two one masses is always going to weigh less than 4 one masses, so the two experiments can't weigh the same, and so it's better to just have them weigh the same difference. That is, to have the same tension on whatever you're using as a pivot, and such. So so I think that's about enough of that. I obviously found more to say in the original video, but I should be done soon. So what else? So again, just the idea is to just say, I'm saying, look, just put it you can use the same masses, and that way you're also eliminating any kind of creation of weird masses. Now obviously you can't make it. It'd be ideal to have them the same size, but then they'd have the same air profile, but the amount of friction from the atmosphere is going to be minimal, I would imagine, so it really shouldn't make any difference. Just trying to make a simple experiment that is clean and decisive in its results, and so that's the ideal that we should all be interested in seeing, and such. So come on, get to the next one. How much could I possibly say about this? Yeah. So anyway, yes, you conserve the momentum. The one mass has to move twice as much as the two mass in the same time, and that's the law of the lever, and it does work, and that's why levers are useful. That's because you can change a big mass going a small v into a small mass moving a big V. Alright, so the second experiment, I was thinking about the Newton's cradle kind of idea, right? So clearly energy goes in, you get energy out in the simplest version of the experiment. We're using the same masses. And as soon as you change the masses, you can't conserve the kinetic energy. Now, they're claiming you do conserve it because somehow momentums cancel, and that you get this huge increase in the amount of total momentum in the system. And that's what conserves the kinetic energy, is you're basically saying energy this way cancels energy that way. So they create a bunch of reflections that'll cancel the energy. So in their version of the Newton's cradle, in the idealization is that you could basically have a small mass hit a large mass and get all of your energy back. That means you'll get a full return, 100% back if it was a pendulum. And so you shot it back into gravity, and you could just hit it over and over and over again forever. And each time it hit, it would give 200% of that momentum. That is twice as much momentum to the object it hit. So this is the taking their theory to an ideal extreme. That's what they say the universe is capable of if you can get rid of frictions, any kind of losses in the system. So and obviously that's ludicrous nonsense, because I could just feed these heavy things in, have them knock out, and the pendulum goes all the way back, and then it hits it another one, knocks it out at 200%, and it just keeps doing that over and over and over again forever. And that's obviously nonsense. Yes, we can't do the idealization, but you can't even do anything even close to that. It's not going to happen. It's junk science, frankly. So I was thinking of ways of demonstrating that this silly notion that an explosion is no energy. So even though you know it's a bunch of energy, even though the momentum going this way and the momentum going this way will do work in the universe, that momentum will hit stuff and move it. It didn't cancel in any way. You can never cancel energy. I mean, if you catch it and it's reflecting, then it's not being used. It's not heating anything. It's not doing anything. So it's only when as soon as you do something with it, as soon as you make heat, you've used momentum. As soon as you do, because it's all just conversion. Heat is just little things moving a faster velocity. The only way they can move a faster velocity is you had to use something's velocity to give them more velocity. Just like you can imagine a big thing can't move unless some little things hit it and move it. And direction is irrelevant. So I use pool balls as an example. If I stacked a bunch of pool balls next to each other and had a pool ball that could go right in between them and knock them all sideways, you wouldn't expect that you could just cancel. You could just pretend all of the energy going sideways cancels, and you don't have to, you don't lose any speed. Of course you're going to lose all your momentum. So if I break I take a cue ball and hit it and break a bunch of cue ball, billiard balls, they're going to leave with exactly the momentum I put in with the cue ball. All right, this part I'm explaining that I could make a Newton's cradle with like a steel rod, a very hardened steel rod, and I could basically bang it in, and I could pop the thing out on the other side. And theoretically, by size, I could make this different sizes, and I should theoretically get a different amount of time it takes to pop it out on the other side, because basically the motion moves at the speed of sound in the steel, the energy, the vibration. And so it's not going some kind of speed of light speed. It's much slower than that. Now, 3,000 miles an hour or something like that, steel is much faster than in air, the speed of sound, but it's still a quite manageable speed. So that would be an interesting, just to show the point. And the point of doing the experiment is my argument is, if I don't put the ball at the other end, right? So if there's no ball here at this end, it should be playing. Oh God, nothing going right today. All right, there, I think it's going, and the microphone's still working. Good. So you put it in, and the other thing pops out the other end, and you should conserve, a substantial, depending on how hard the steel is. If you're lucky, you can conserve, 90%, something, maybe. And you could just basically make a Newton's cradle with this big piece of steel in the middle. Theoretically, that should work. All right. If it doesn't move, it has to be heavy enough where it doesn't move itself. So that's the catch to it. But it shouldn't move, because actually it'll hit this other mass and give it the motion, and so it shouldn't be a problem. So the theory is that if I don't have this one at the other end, and then I'm going to get the reflection. So I get no reflection if this one leaves. And if I don't put one here, I do get the reflection. And the reflection is basically should be at the speed it bounces off the other side and then goes back. So it should take a while for it to reflect, depending on how big this piece of steel is. Now, theoretically, yeah, maybe the steel knows right at the surface that the atoms aren't going to move, and so it knows to reflect it. but you're almost saying it can't know, because in the Newton's cradle, it goes through 5 or 6 balls and then gets to the end ball and says go. So how does all the other balls know that they are not supposed to move? Well, they can't is the point. And so anyway, it would make for an interesting experiment, because first you would demonstrate that a reflection, okay, is the original thing's energy. It's not new energy. It's the energy of the thing you put in. You're just getting it back again. You're not putting 200 into the steel and then getting 100 back for a net 100, okay, but you're doing your silly subtraction. You're just getting back what you put in. What you put in goes all the way to this end. The electrons pop out at that end, and they don't have anywhere to go. Nothing's connected to them. So they just pop back in again, and the energy just moves back. So that's what I'm illustrating there. It just goes to the end, comes back again, and the ball takes off because it's getting hit with the same energy it put in. So it put a vibration into the steel. The vibration takes a little time to figure out it's not going to be able to go in that direction, so it just reverses the direction, because the electrons are elastic. As I pointed out, atoms are elastic. You squish an atom, it reforms its shape. You can't, if you put energy into an atom, it'll tend to restore itself. And so the argument is, if I make this different length, I should get a different time for the reflection. That would also prove that this F equals ma crap they worry about, this always measuring the rate at which something accelerates, doesn't have anything to do with anything. Okay, it's not going to be about the rate of acceleration. It's going to be about what is just the net force. And the speed with which the net force pushes the object isn't going to make any difference to the fact that it's going to pretty much, once the energy comes back, it's just going to instantaneously have the same velocity it hit with. It's not going to slowly accelerate, because that's not what Newton cradles do. They don't slowly accelerate. You don't put the ball in and it decelerates and then the other ball accelerates. That isn't really what's happening. It's a clean transfer of the vibrational motion inside the steel. So my other version of this is to take a tube with rubber at either end and a fluid inside, okay, and then do the experiment, because that should not be perfectly elastic, in the sense that you shouldn't get all of the energy to move through that pressurized fluid. And so what you'll get is some reflection and some forward motion, and that will demonstrate that the reflection is what you're missing here. So whatever you get here, 60% of the energy comes out this side, then 40% is going to reflect on the other side, that kind of thing. So it will be a way of demonstrating it. And if you change the shape of it, would also be an interesting experiment, just because that should be changing velocities, or the portion of the energy that will go one way or the other. And so that might make the experiment also quite interesting to see what the proportion of momentum that's transferred in the different experiments. But clearly it's another way of transmitting the energy from one object into another object, and to do it at different MVs, basically applying the force over different amounts of time, and with different aggressiveness, I don't know what the right term would be, at higher or lower pressures, I don't know, per square inch kind of arguments. I don't know if that could make much difference, frankly. But anyway, it's just a way of another way of doing the experiment, and just recognizing that all you're doing is transmitting energy from one impact into another impact. There's two objects connected to each other, and that's all you're really saying is you're connected to, and then you're going to disconnect to. And the simple argument is the momentum in absolute terms has to be conserved. It's just about how much mass is moving in the universe. It's not about what direction it's going. Direction can't matter. And again, the pool table proves it. The pool table is telling you it doesn't matter what direction it is. You hit the cue ball into the 15 balls, they all scatter. If you add up all their little momentum arrows, it'll add up to the one momentum arrow that went in, and direction is irrelevant. There's no canceling directions. It just matters that there's motion. There's mass moving, and that's all that ever is going to matter. So is it really your argument that when I collide the cue ball in, that somehow I'm going to make more kinetic energy? That I can get more energy out than what I put in? I can't. Yeah, no, simple truth is the high velocity of the cue ball is not going to be represented in the slow velocity of the masses that will result, and I won't conserve the kinetic energy. And the fact is I do have to conserve the momentum, and direction won't matter. So there's no room for argument here really by reasonable people. I don't know. As stated, I just think it is all just a religion to these scientists. They're not really very good scientists. It's been, a couple of different science presenters have admitted that, it was the Wooey double slit experiment that got them interested. This is really the core of it. They wanted a physics that wasn't mechanical, reliable by rules, something that, it's almost back to Descartes. She was basically a free willer, and she believed in this spark of life and this whole idea of a living force and, this wooey crap. And, it's not good science, and it's arguable that it's girly, it's silly. It's you just want you want a god in your universe, and so their god is randomness, or their god is wooey possibilities, or something. I don't know. I don't see the appeal, so I can't talk about it really, because I can't understand it. I can't understand why people think babies are cute, and I can't understand why they're smelly and disgusting. Kittens, puppies, they're cute. Human babies, ooh, creepy. Anyway, and I can't really understand why they want physics that is full of mystery and magic and wonder and all that bullshit. And it's just that bullshit. So, I was pointing out that, look, you can just figure out everything's just made out of little atoms. You just count the atom masses and you count their motion, and that's it. 1,000 atoms moving 1 mile an hour is the same as one atom moving 1,000 miles an hour. It's going to transfer the same amount of MV into the universe. And all we're looking at in all these mechanisms is some way to turn a small mass going a big V into a big mass going a small v, and it's always going to be the same. Those numbers always have to add up. The system always has to have that amount in it. That's how the universe works. It has a certain amount of motion, and all of the motion has some mass. Even the little bits of force have a mass. And you just add up all of the masses and all of the velocities they're going, and that amount of motion will always exist. And there's no entropy problem, so I don't even want to get into that in this video, because I saw another silly entropy video. And again, not conceding that gravity is doing the opposite of entropy. It's organizing matter. It's smashing it closer together and forcing it into arrangements. And that's clearly the exact opposite of chaos and disorder. And so you have an obvious mechanism that's restoring the amount of entropy in the universe constantly restoring the order. So the universe is not going to dissipate into chaos as long as gravity is there to keep consolidating it and pushing it back together. So again, that's another simple principle. You can't argue this with scientists. You know, they won't. Yeah, I mean, they're non-responsive. You can't provoke the argument. You can't get a counter-argument in any rational form. Just cartoons that are off the subject, and you know, it's just a really bad circumstance. You know, that after years of presenting all of these contradictory statements by their physics, you have to conserve momentum. No, you have to conserve kinetic. No, you have to conserve energy. No, you know, all of these different, you know, this bullshit terminology that somehow energy isn't torque and it isn't force and it isn't this, and you know, when it's all energy. Heat is energy, force is energy, torque is energy. It's all energy. It's all necessary that it involves pieces of matter moving, and that has to be conserved. Alright, so I think that's enough and such. I seem to still be rambling on in the video, but that's okay. It's almost towards the end. So this video will be a tiny bit shorter, which is okay. So I might as well stop that one and finish this one. So anyway, till the next time and such and so forth and whatnot. I guess I could just, let's see, is this that? Yeah, it is that. Okay, so I could shrink it. So yeah, that was the video. Anyway, so till the next time and such and so forth and whatnot. Blah, 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 blah. I hate this planet.